In this video, we're going to talk about functions. So let's define a function. And you've probably seen this at some point before in algebra, but we're going to start doing a more formal, mathematically advanced definition using some of the terminology we have begun to develop in this class. So let A and B be non-empty sets. A function f from A to B is denoted using this notation. This is like a functional notation. And when I say functional, that's a bigger word than the functions we're even talking about right now. That functional notation, so where we're saying f is mapping A into B, is an assignment of each element of A to exactly one element of B. In fact, let me highlight that. That's an important statement right here because this is the big key for a function. Each element of A to exactly one element of B, the exactly one element of B. Okay, we write the notation f of A equals B if B is the unique element of the set B assigned to the function f to the element A of A. Okay, sometimes functions are called mappings or transformations, and you heard me say map A into B a second ago. So yeah, those are also words we use when we are looking at this notation. Okay, let's just look at some examples of functions and verify why they obey this definition of exactly taking an element of A to exactly one element of B. So the first example is assigning values, as you see below. In this particular example, it's grades in a class, and they did it by last name, so each student is getting a grade. Okay, this is a function because an element in A, which in this case, A would be the students, all right? And B would be the grades using our notation above, okay? Each element of A is going to exactly one element in B. In other words, a student isn't going to get two grades for the class. They get one grade and one grade only. That's why this is a perfect example of a function. Okay, another example would be this formula. F of x equals x plus 1. That's because if I plug a number in for this formula for x, like 2, I'm going to get out only one number every single time. In this case, 3, right? 2 plus 1 is 3. So the idea is if I look at an element that I'm allowed to plug in our domain, in this case, the implied domain is the real numbers. Any number I plug in, I'm only going to get one number out. So it's a function because each element in the domain gets assigned one answer, one element in the range. The relation A cross B can also be thought of as a function because you might recall when we talked about A cross B, this is that relationship where we have elements of A and elements of B, right? And we are creating ordered pairs with those elements. The idea, though, is that we would be looking at A as the assignment, and then what it's getting paired with in B, that would be our notation that we would use f of A equals B. So it does have that functional relationship. Okay, I'm going to switch back to my red pen now. So we're going to look at some terminology. And I kind of set this up as fill-in because I thought that'd be a little bit more interesting. So let's say we have the function f mapping A into B. We say that f maps A to B, or f is a mapping. So this is an opportunity to write the language down from A to B that I just said. A is called the domain of f. Now, of course, I'm sure you've heard the term range, but we won't be using that terminology. We're going to use the terminology codomain. And the reason has to do with what we're going to be looking at soon. And that's the idea that we could go back and forth between A and B, how we decide to set up the mapping. Okay, so we're going to call it the codomain. They like that terminology. It kind of fits a little bit better for us. Okay, now real quick, just to kind of draw that out. Here's the idea. Here is our set A. here is our set B. And the idea is we have this element in A, we'll call it lowercase a, and an element in B, and a function that takes A and maps it to B. That is the function. And A would be the domain, B is the codomain. Sorry, I just realized it was kind of a crummy looking B. Let me fix that. There we go. A being the domain, B being the codomain, and F relating the elements between them, but only assigning A to one element in B. As long as that stays true, we're good to go. Okay, let's keep going. We have some more terminology here. If F of A equals B, then B is called the image of A under F. That image terminology actually plays a little bit into calculus for anybody who goes into calculus. There's this kind of idea of images and projections. So yeah, it's kind of playing with that that verbiage for making up a way of saying that way of describing it. Sorry. A is called the pre-image of B. So image is the item that we're mapping to, right? The B that we are mapping to. Pre-image is the item that took us to that image. All right. Now I mentioned it, but it does count as terminology we know. The range of F is the set of all images. So we're saying, rather than saying that B is all of the range, it isn't. We're specifying that the range is going to be specific values in B. All right, specific things that we're looking at in B. I'll give you an example in just a second of how that works with some problems, but we'll talk about that in a moment. Okay, so two functions are equal when they have the same domain, the same codomain, and map each element of the domain to the same element of the codomain. I know that sounds kind of funny, but it's true. That's how they define two functions being equal to each other. Okay, let's look at an example here. We'll kind of get some of this under our belt, this language. Okay, so first thing I ask is for us to find F of A. So looking at this picture over here, figure 2, F of A is going from, here, I'll use my highlighter, A to Z, right? So the answer would be Z. Oops, Z, just kidding, not that. Okay, what is the image of D? Image. So image is figuring out where when we look at what's paired up with D, what D gets paired up with. So it is kind of the same question as part A. So the image is the result that we get in the set B. Okay, so there we go. D is going to Z. So actually I could have put the Z there. Okay, now what is the domain of F? Okay, well, in this case, the domain would be the set A. Capital A for representing the set. If you want to, if it makes you feel better to say the set A, you could do that. What's the codomain of F? That would be the set B. Now, it's not mentioned here, but let's take a second and talk about it. The range would not be B. The reason is X is in B. Oops, wow, sorry, I selected highlighter, but didn't get it. X is in B, but nothing in A is mapping to this X. So the range is actually only Y and Z. All right, so that's just kind of making a distinction between domain versus codomain. So codomain is the set that contains those elements. The range is the actual elements we're mapping to. All right, so a little bit of a distinction. Okay, Pre-image. Okay, so now we're looking at the B. We're looking at an element in B, in this case Y, and we're seeing mapping backwards. So that would be the point B. And then the pre-image of Z. Okay, well, that actually is a little bit more complicated, right? The pre-image of Z, there's actually, oops, I'm so sorry. I thought I had the highlighter done. The pre-image of Z is actually 3 different elements. So we would list all 3, A, C, and D. Okay. Oops. We will refer to this example again in just a moment, but let's look at another terminology that I wanted to talk about. So if F maps A into B and S is a subset of A, then the image of S under the function is the subset B that consists of all the images of the set S. So let me let me write this a little bit cleaner using some of the writings we have seen, the set builder notation. So F of S is all T such that there exists an element S in our subset S where T equals F of little s, that element. So T is the pairing up with the S in our subset. There is a shorthand way of saying this. F of S equals all S, equals all F lowercase s. So that's capital S. This is lowercase s. All F of S such that S is an element of the subset. So the idea is we're saying that we're only looking at images that are coming out of the subset. Okay, so let's do it as an example here. Using the function from figure 2, find F of S where S is A and D. So A and D are the elements we're interested in, and A and D happen to map to Z. All right, so that would mean then that the function F of S is going to equal Z. Oops, I'm so sorry. I clicked something on my pen and it got very mad at me. Now I want you to notice, this is a capital S. I know it's kind of hard to tell with my scribble here. I wrote set notation, and that's because F of S denotes a set. So I'm not saying F of little s equals Z. I'm saying this whole set equals Z. Really quick, let me just expand on that. Let's say I made S B and C this time, B and C. So I'm picking the other 2 letters, okay? Then F of S is going to equal, let me come back up here. Let me erase my highlighter here. So B and C this time. So B goes to Y, C goes to Z. So Y and Z are the images. Oops, I wanted to do it in green to keep it separate. So Y comma Z would be the answer. That's the set that B and C are mapping to. So we could say that F is mapping BC to YZ. That's one way we can use that notation. Or we could say that F takes S and maps it to YZ. And YZ, by the way, is a subset of B, the codomain. All right, so there we go. Whew. Hopefully that makes sense, that notation. Okay, we're going to look at one-to-one and onto functions. You might have seen this before. Again, we're going to kind of change it a little bit just because we want to add some terminology that's important for computer science. A function is said to be one-to-one or injective. So that's the phrase that I'm assuming, by the way, is associated to computer science. I've actually never heard of it before. So I'm just assuming it's a computer science association. Maybe it's not, maybe it has more applications, but we can use the phrase injective instead of one-to-one. If and only if we say that two things are equal in our function, that two different values come out with the same image. So I plug in A and I get out a value, and I plug in B and I get out the same value. All right. That implies that A equals B. Okay. So take a second here. I want to come back to this example. It's a good example. In this case, if I plugged in f of A, that happens to also equal f of C in this example up here. Do you agree? Because f of A is Z, and so is f of C. They both come out equal. However, A and C are definitely different elements. Do you see that? That means that this function up here is not one-to-one. Okay, this would not qualify as a one-to-one function. All right, just to kind of explain that a little bit more. So, this is an example of a one-to-one function. The idea being that each element in the domain are not mapping to the same elements in the range. So it's possible to have a function where elements in the domain map to the same thing in, I'm saying range, but I should say codomain, sorry. The elements in the domain are mapping to the same thing in the codomain, like we saw above, all right? They still stay a function, but they're not one-to-one. So as long as the elements in the domain go to only one element in the range, and they don't both go to, like, we don't have two elements in the domain going to the same element, that's one-to-one. So let me write that down. No two elements in domain go to the same element in the codomain. All right. Onto. A function is said to be onto or surjective if and only if for every element B in our codomain, there is an element in A that goes to it. So in this case, we're saying that all of the elements in our codomain are being used. So they have something mapping to them. So every element in the codomain is paired with an element in the domain. Okay. So we're going to relate both of these in just a second, the two concepts, and make sure we understand the difference. Okay. Real quick, just because we did just talk about it. This function wouldn't be onto, and the reason is two elements in the domain are going to the same element in the codomain, and that's a problem. Up here, this example, this is not onto, and the reason is there's an element in the codomain that isn't paired with something in the domain. Okay, so there's two kind of ways of discussing that. So before I do some more examples of that, really quick, when it's both one-to-one and onto, when it's both one-to-one and onto, we call that a one-to-one correspondence, or the book gives this phrase bijection. Okay, a bijection means that it's both surjective and injective. Okay, one-to-one correspondence means it's one-to-one and onto. Okay, so here, let's look at an example here. Sorry. Okay, let f be the function from a, b, c, d that maps to 1, 2, 3 and is defined by f of a equals 3, f of b equals 2, f of c equals 1, and f of d equals 3. Is this an onto function? So I'm going to do our picture because I feel like our picture helps. So here's the first set, A, B, C, D, okay? And so in A, this is A, B, C, D. And this I'm referring to as our domain, right? Which we could call capital A if we wanted. Okay, then our codomain here is 1, 2, 3, those elements. And here's the mapping. F of A is mapping to 3. F of B is mapping to 2. F of C is mapping to 1. And F of D is mapping to 3. Okay, so it's not onto. I'm sorry, it's not 1-to-1. I'm just going to say that real quick. It's not 1-to-1. By the way, see that? That's a shortcut notation for 1-to-1. Because mathematicians are lazy, so we create shortcuts. So 1-1 means 1-to-1. Okay, it's not 1-to-1. And the reason is A and D are both going to the same element in the codomain. So that's problematic. Let me go ahead and boop, get rid of those. Okay, now it is, however, onto, because every element in the codomain has something mapping to it. So the answer would be it is onto, because it satisfies that everything in the codomain has something paired up with it. Okay, oops, let's look at another example. Sorry, I keep bumping the screen and it's getting very mad at me for that. Give me a second. I'm going to attach the keyboard to make it happy again. Okay, I know you're so pissed at me. I'm such a jerk. Okay, there we go. Gets very mad and sensitive. Okay, so is the function f of x equaling x squared from the set of integers into the set of integers onto? Okay, that's a good one. Okay, so first thing I want to do is remember that the integers are the numbers that include the negatives. Oops, -3, -2, -1, and it's dot, dot, dot to negative infinity, and then 0, 1, 2, 3, dot, dot, dot to positive infinity. So it's this set of positive and negative whole numbers, okay? So the idea is that's the integers. And they're asking if it's onto. So remember, onto means that the codomain, every element in the codomain is being used. So this is the codomain, okay? Because we're saying it's from the integers to the integers. We're assuming that it's taking z, oops, that's what we use to represent integers, z, and mapping it into z, okay? So the codomain and domain are both the integers. And the problem is, if I plug like -3 into this function, I'm going to end up getting a positive 9 in particular, right? Same thing as if I plugged in +3. But that's a problem because basically I'm never going to get a negative number. None of these negatives are going to end up coming out of the function because of the squared. The squared is the problem. So we could say, a way of saying this is to say that there is, oops, it helps when you use the pen and erase, thank you. There is x in the integers where x squared equals like -3. There's nothing I'm going to be able to plug in that's an integer and it's going to pop out -3. So it's not 1-to-1. Therefore, not. I'm sorry, onto. onto. This is the therefore symbol. I don't know if I've ever used it in this class yet, but I use that sometimes to write conclusion, especially if I have a lot of work written down. It helps me kind of summarize what I'm concluding from my discussion here. Okay, so it basically means therefore, those little 3 dots here. Let me just highlight it. This means therefore. Okay, you might have even seen that before. It might not be new to you. Okay, let's determine which of the following functions are one-to-one, onto, or both. Oh, first, actually determine which of the following are functions. Okay, so first thing we got to do, we haven't done that yet. Talk about making sure that something is a function. So remember, a function only maps to one thing in the codomain. Okay, so looking here, everything in set A, right? Everything in set A here is only mapping to one thing over here. Okay, so we're good. I should say domain and codomain. Same with B. We're good there. So here, sorry, let me go ahead and write that this is a function. This one's a function. This one's a function. This one's a function. Here we go. Not a function. Okay, so all of them are functions except part E, which makes sense because we can't talk about them being one-to-one or onto if it's not a function. So I'm not going to look at part E anymore when I'm talking about things being one-to-one. It doesn't matter because it has to be a function to be one-to-one. Okay, so let's look at the first one. So one-to-one means that we're not having 2 things in the domain going to the same thing in the codomain. Okay, so this first one is one-to-one. I'm going to use my shortcut notation there, one-to-one. We're good on part B. That one is, oh, wait, nope, sorry, just kidding. That one's problematic because D and A are both going to 2. So this one is not one-to-one. Okay. Let's see this one. Oh, that one's one-to-one. Okay. Let's see. This one is not one-to-one, right? Those 2 both went to 2. So not one-to-one. And then I'm not going to look at part E because it's not a function. So there's no reason to talk about one-to-one or onto. Okay, now onto is looking for whether all of the elements in the codomain are being used. And right off the bat, in this first one, I see that 2 is not used. So this is not onto. So it's only one-to-one, but it's not onto. Okay, the second one for B, all of them are being used. So this one's onto. So here's an example of something that's not one-to-one, but onto. The first one is an example of something that's one-to-one, but not onto. Okay, the third example, this one's onto. So here's an example of something that's both one-to-one and onto. Nice. But the fourth one, D here, is a problem because that number 4 did not get paired up with anything. So this is not onto. So it is a function, but it's not one-to-one, not onto. And the last one is an example of not a function. So we won't even bother with whether or not it is one-to-one or onto.